specifically about that Life is Short video or series, which has been the bane of my existence. Anyway, I've gotten to a point about Rayleigh's criterion, and I'm trying to marry ray optics or Gaussian optics with wave optics, but I keep running into a problem. Um, Apparently, the rays are always perpendicular to the wavefront, even if the wavefront is a curve. I know you don't like that, so I'm trying to figure out how to do this. Any suggestions?
The rays are always what? Perpendicular to what?
They're always to the wavefront, and the wavefront is a curve.
Bro, I barely know what you even said just now.
Basically, rays, light rays and wavefronts, right, that carry them are always perpendicular to each other. Now, you said you can't have perpendicular to a curve, but that's like every definition I found is the ray is always perpendicular to the wavefront curve. So I was wondering if
I
you had
didn't say you
suggestions on
can't.
how to go forward.
I didn't say you can't perpendicular to a curve. I'm saying when you describe level being perpendicular to plumb, that's very vague and unspecific because that could also be concave Earth or flat Earth or globe Earth. Like you're not describing anything when you say that.
Oh, sure. Yeah. I thought that was, oh, well, then I'm glad that's not the issue. Yeah, level just means with regards to a reference. If the Earth is flat, then level and vertical are going to be two straight lines, right? If it's a
You
curve of
would
any kind,
you would
globe or
just
concave.
if Earth was concave or flat or globe, you could describe it the same way you guys say, and it would just be the same. Like there's no like when you say it's perpendicular at a point, that could be curving up, right? Why can't it be curving up like concave Earth?
Well, for other reasons, not just for the reasons that they intersect at perpendicular, right? Then we got to see, is it curving up or is it curving down?
Yeah, we know, but when you describe it like that, you're not describing anything because it could be concave or convex or flat. Like you're not really saying anything when you say that. It's
Yeah,
perpendicular at a
no, that's absolutely correct. Yes. The reason that was brought up though was to address the conflation between level and horizontal, right? That's the only thing really that I think there was a problem with was assuming that level was horizontal.
Yeah, but you're not by saying the thing you're saying, you're not solving the conflation because the thing you're saying could be the same thing.
It could be, but it's not necessarily.
But you agree when you say that you're not really saying anything? I mean, I think you just agreed with that.
I'm just saying that level isn't necessarily horizontal. That's the only thing I ever meant to say with that whole thing.
Yeah, but when you say that thing, it describes horizontal as well.
It can, but it doesn't necessarily. It's horizontal if the reference is flat. So if the Earth is flat, then level is horizontal.
If we went out in the street and I asked people to draw a perpendicular at plumb, to plumb, whatever the word game is, we went out in the street, what do you think they're going to draw?
Probably draw a cross, vertical and a horizontal line.
Yeah, they'd probably. I'd have to imagine everyone would, right? Do you think anyone would draw curving up or curving down?
If you got someone eccentric enough, they might, but I'd say it's probably unlikely. I think anyone who's been in this conversation for any amount of time might do that. Otherwise, probably not.
You think if I asked Zanuck or Kosho or someone, they would draw it curving? If I said, "Hey, draw perpendicular to plumb" or whatever the phrase is, you think they would draw it
They
curving?
probably, I think they might, yeah.
You're just not describing level on a globe when you say that, because you're also describing level on a concave Earth and level on a flat Earth. So like, there's no description of what you think level is when you say perpendicular at a point.
Sure, but that wasn't what was in contention. Like again, that was really just to dismount the level is definitionally the same as horizontal, which has always kind of been an issue of, I think, circular reasoning in flat Earth. Like once we've gotten rid of that, then we can talk about how things can be level, but not horizontal. Then we can talk about if it's curving up or curving down, or curving at all, for that matter.
Well, doesn't that all kind of rest on whether or not there's a center of gravity on whatever we're on? I think we
If
also
level
don't.
down, yeah.
Yeah, like we don't. I don't think you and I agree that mass attracts mass.
I suspect we wouldn't. No. You think it's electrostatics?
Sorry, say that again.
I was asking if you think it's like electrostatics or something, or ether drift.
No, I have no idea.
Oh, okay.
I just don't think it's mass attracting mass. I've never seen that.
What's going on? What's the topic?
Gravity, I think, or the lack thereof.
Dielectric mutual mass acceleration. Just as simple as that, bro.
Super simple.
Super simple, bro.
Can you give that to me in like dumbed down English?
English, use English. Yeah, that shit don't sound super simple.
English?
Yeah.
Let me pull up the Ken Wheeler definition here for you. Okay, he says gravity is not a unique or autonomous field modality. It's the very same phenomena that we call electrostatic cling or magnetic attraction, which is the very same phenomena we call gravity. He says, furthermore, objects do not accelerate towards one another as perceptually witnessed, rather they accelerate towards the lowest null pressure point between the two. And the same is likewise for the case of inverse polarity magnets, where it's seen under a supercell that a portal in counter space is generated between the two, which the magnets are moving towards it, not themselves, but rather this null point. It's
Well,
also said
that clears it all up.
oh yeah. He says the difference between so-called gravity and so-called magnetic attraction is that in the case of magnets, they're multiplicative point source objects accelerating. So the intensity is many magnitudes greater than that of common objects accelerating towards the null point in counter space. He says mere masses of the conventional kind are point non-specific or incoherent objects. He says gravity does not exist. Gravity is not a force. And basically, it's dielectric mutual mass acceleration.
All right, to get anything out of that, I would have to have you define like 10 extra terms now. But I did want to focus on one thing you said. You said the objects move towards the lowest null pressure. What does
Yeah,
that mean?
the lowest null point between the two objects. So I think a couple of years ago there was like an observation, a celestial observation that took place where these two stars came in very close proximity of one another, and for quite some time they literally spun around each other before they actually came together and touched. and that's like the antithesis of geomagnetic precession. Um, so essentially, basically, masses aren't necessarily attracted to one another, rather than this null point between the two. And you're asking about the null point between the two,
Hmm.
which is essentially field friction between the magnetic and the dielectric, in which magnetic generates phase, which is why there's a proportional disparity of a ratio of 1 to 5 between the north and south pole of a magnet, and eventually enough torsion that causes flips of polarity over time. So hopefully that answered it.
Uh, kind of. But I wonder, like, is this also true with magnets? That magnets aren't attracted to each other; they're attracted to like a center point.
Yeah, exactly. Magnetic attraction actually doesn't exist. Magnetic repulsion is really the only phenomena that does. So, in
Interesting.
terms of magnetic attraction, it's a misnomer that magnets come together. Um,
I've seen them come together.
magnets don't accelerate towards one another. Like I said, rather towards this lowest pressure point, which would be like the vortexual center between the two. Um,
But that center can move, right? If I keep one of the magnets still, then the other magnet is gonna go all the way to the first magnet.
well, that's the thing. Like, it's a misconception that magnets, like magnetism, that magnets emit magnetism. In fact, it's the opposite way around. The magnetic field, the magnet sets up a field disparity in the already existing magnetic field. That's why they call it a point source object. Um,
I feel like this is all kind of the same thing with extra steps. Like, is there any benefit in representing it this way than just saying that the magnets emit a field and the field affects the other magnet? Like, what would the difference? I I don't know. I'm curious. Like, what would it look like if it was just magnetism, like a magnetic attraction?
well, that's what I'm trying to tell you. Like, if you were to take a Gauss meter to a magnet, to the center of like either the north or south facing side of the magnet, it's going to read 0, because magnetism actually resides at the edge of the magnet, which is the plane of inertia, and that's the effect that we call magnetism. The repulsive and the attractive side isn't actually at the face of the magnet. Like, if you were to hold a neodymium magnet in your hand close to something that's like ferromagnetic, you would see that the intensity of that magnet pulling towards that ferromagnetic object is going to intensify as you turn the magnet to its side rather than, like I said, the north facing side. So that's all basically what I'm saying.
All right.
It's yeah, it's basically torsion, where rather than a force dissipation, the force is a multiplicative, and in my opinion would be like the most basic definition of unnatural.
Right. So let's say I give you all that, because I'll be entirely honest, I maybe caught half of that. Um, if we can measure the magnetic field of a magnet, whatever that's actually representing, why is that not present in things that aren't magnetic, that are still attracted to each other?
What was the last part of your question? You broke up a little bit.
So we can measure the Gaussian field of a magnet, say, right? We can see that there's a correlation between that and the quote unquote attraction between them, whatever that actually is. Why is that not present with things that aren't magnetic?
Because the magnet itself is, like I said, it's a point source object, so it's affecting the already existent magnetic field. Like I said, if you were to take a Gauss meter to a neodymium magnet, roughly at about 2 feet, the reading would fall off. You wouldn't be able to pull the reading anymore. All right. But if you were to take like a CRT television tube set, like an old school TV, and you were to take that neodymium magnet up to about 100 feet and you were to wave it across that tube set, you would see the field disparity across the tube set at 100 feet. Now, why is it that you're seeing the effects of that magnet across that tube set at 100 feet, but you're not able to pull a reading of the magnetic strength with the Gauss meter?
No idea.
That should tell you. That should tell you that the field is already existent, and it's the magnet affecting the field, not the field emanating from the magnet.
Sure, but why do we not see that if we wave like a plastic ball in the same way?
You
Even
can.
like very close to the.
I can take a number two pencil and get it to stick to a vertical wall with electrostatic cling or field friction. I could do the same thing with a piece of plastic or a piece of rubber or a piece of metal.
Right, but you have to like do stuff to it. Like its natural inclination is going to be to fall, right? Unless you charge it, and then sure, it'll stick to stuff.
I don't even have to charge it.
Seems to be too.
I could literally take that pencil and press it to the wall. I might have to drag it like a quarter of an inch to kind of set up that electrostatic field friction and what you called charging it. But again, the effects are the same. You know
Well, I don't
what
think
you
they are the
call
same.
what's that?
I don't think they are the same. Like one is very strongly correlated to the amount of mass the thing has, and the other is very strongly correlated to the charge it
Well, I mean, do you think a living frog has a charge?
has. I would assume it might, yeah.
Would that charge be sufficient enough to defy gravity?
It shouldn't be, no.
So what if we put that living frog in a level 3 Tesla field and got that frog to levitate while still living?
I think you've affected the charge. You could have given it an extra charge or something. I honestly don't know what a level 3 Tesla field is, but from the
Well,
sounds of it, it would be like what you do with a piece of plastic or the rubber.
yeah, this was performed on a university where they took strawberries and a living frog and were able to levitate them in a strong enough Tesla field. So
Yeah,
that's what
in
I'm
a strong
saying.
enough
Like,
Tesla field.
what?
In a strong enough Tesla field, you said.
Yeah, level 3 Tesla field. Correct.
Right.
But
So you don't
well,
seem to
again,
need to do any of
but
that
again, we're not
for
talking
things
about a
like this.
ferromagnetic object now, are we?
Sure, and that's fine. But
So that's
you
what
can
I'm trying to
charge
tell you.
anything.
Everything in the universe, be it ferromagnetic, diamagnetic, or paramagnetic, everything in the universe is magnetoreactive.
Yeah, but that's going to be related to something other than its mass, right? You can have two objects of the same mass and have them behave differently in a field, in an electric field.
Okay.
But those two objects, if they have the same mass, right? The attraction between masses seems to be correlated to the masses itself, right? To the mass itself is what I'm saying. Whereas what you're talking about is correlated to something other than the mass.
So in your mainstream model, gravity affects light, does it not?
In a roundabout way, yeah.
Okay. And is light a massless particle? There's no rest mass
Uh,
to a
in
photon, is there not?
theory, in theory, yeah. We
So
can't
how could
register mass with the lowest instruments we have, yeah.
okay, so if you've got the effects of gravity upon something that's massless, considered to be massless, then how could that not then correlate to what I'm telling you in terms of magnetism being considered the same thing, the same effects of gravity? Why would you assume that mass would be the defining factor of something either having attractive or repulsive nature to it?
For the same reasons. It seems to be correlated to the mass of the object deflecting it, rather than the charge of the object deflecting it.
I don't know what you said, but I missed it.
Light bends according to how massive the object is, rather than the charge of the object.
Light bends according to how massive the object is. And then what was the last part?
Rather than the charge of the object.
But we just went over the fact that there is no rest mass to light.
Yeah, and if you with gravity, right? If you substitute all the numbers, um, I have to do it on paper, but basically, if you have two masses, right? Let's say you and something else, your mass gets canceled out, right? The only thing
And
that really matters is the mass of the thing attracting
when you say mass, like which of the 16 definitions are you going with so we can be on the same page here?
you. For this conversation, I would say it's the amount of stuff in a thing.
The amount of matter?
Yeah.
And then what defines matter? Is it the amount of mass? So you've got a circular
No,
premise.
no. Matter would be, I honestly, I've never thought of how to define matter. I would say it's,
Well, it's
that's,
often referred to as the circular reasoning in the sense that mass is dependent on matter and matter is dependent on mass. And this is kind
well,
of
they
why
could be,
we're at a standstill.
sure, they could be dependent on each other, but I don't think I would say they're the same thing. You can get mass from matter. I don't think you get matter from mass. Does that make sense?
Can you have mass without matter?
No.
Are you sure about that?
No.
Do
That
you
was
realize
awful
do you
example.
realize that do you realize that an electron, a single electron, has no spatial volume yet has mass?
Okay, yeah, that is fair enough.
All right. Now, can you have matter without mass?
Yeah, matter without mass. Um, I suspect not, but if you hit me with another interesting fact, I might change that answer.
Well, like I said, it ultimately depends on how we define mass. So, based on how you define it, will kind of determine the outcome. So, if we're just going to leave it very vague and ambiguous and say that, you know, matter and mass are, contingent upon one another, then I don't think we're really getting to an ultimate rational explanation. So, I would
Well,
use a
that's
different
fine.
definition personally.
Sure. I mean, that's fair, but would you at least agree that mass and charge are two different things, whatever mass may be?
Yeah. Yeah, I would say charge is one of those things that hasn't been defined by science. I don't think any branch of science has accurately defined charge, i.e., energy, be it kinetic or potential.
Right. But we can still measure the charge of an object, right?
What do we
Well,
define?
the units of measure isn't an explanation as to what charge is. Like, sure, we can
No, no.
quantify charge.
Yeah, that's all I'm interested in. We can quantify it. And if we
Sure.
Yo,
can
son.
measure the mass of something, real quick, if we can measure the mass of something, right, we can determine whether an effect is correlated to its mass or whether it's correlated to its charge. Even if we don't understand fundamentally what these things are, and we can distinguish that forces acting in correlation to one or the other aren't going to be the same force.
Well, the problem with that is you have a thing that's called potential charge, which isn't charge in actuality. So unless we're just going to discard that, then I think your understanding might work. But problem is we can't just discard that fundamental fact.
Yes, we can, because you just made up this charge.
Oh God, here comes paid NASA show. Is that paid NASA show? Yeah.
Yep, you're just making
There goes
shit up, guy.
conversation.
Oh, you know, you want to make up some shit? Go right ahead.
So
No
listen,
one's making anything up, bro.
so at what point do we consider something not to matter? As in, at what point, where do we draw the line and say that's material and that's not? That matters and that doesn't. What would you consider is not matter? Would you consider a force that is invisible that you cannot detect? Does that make sense? You know, if everything is everything, then in a different form, then everything is matter. Is it not? You know,
Are you trying to say Black Lives Matter? Is that what you're saying?
black light. But I don't know. I mean, the molecules inside the area that it's in, and it's got all gases and stuff like that. Those all matter, are they not?
It gets real fuzzy when you're talking about electrons, because they'll say it has no volume, but it has mass.
But it's got a spatial. It can only do what it can do at a certain distance. So it does have a potential, whatever field. I don't know, but whatever. I mean, where do we draw the line at what matters and what doesn't?
Actually, I would say that is a good line to draw. So when you said an electron has no volume but still has mass, I would suspect that's the different definition of mass than the one I was going with. Like when I was talking about the amount of stuff, the reason that mass is defined also as the resistance to inertia is because when you have things that are moving at like relativistic speeds, that mass can change. So I suspect it's the motion of the electron or something like that that gives the electron mass rather than its substance, so to speak.
Yeah, mass is so terribly defined in science that, I mean, it's just all over the place. But the electrons is what's up?
No, I was agreeing. It kind of is, yeah.
Yeah, it's like your perpendicular and plumb thing is just all this loosey goosey stuff, man. I'm trying to get specific and to the point. You know what I mean?
Well, we were kind of getting there.
How can you have a volume without mass? Is that possible?
No, there's no volume with mass.
No volume, but mass.
But it has mass. Yeah.
And what is this
So
mass
when he asked,
consisting of?
so when he asked about the photon, right, he said it's massless. Technically, we don't know that, right? The lowest, the smallest amount of mass, I believe, unless this has changed in recent times, that we can measure is something on the order, I'm going to get this wrong, but it's something on the order of 10 to the negative 18 electron volts, I believe. So the fact that we're measuring mass in electron volts should tell us something about it's probably one of those definitions of mass that isn't like the substance of the thing. So I don't think it has to have a volume necessarily. Like it can still have like be based on momentum or something like that. This is not my area of expertise, by the way. I'm kind of guessing.
How can you have something without volume? Think about it.
With mass.
I don't know. Does light have volume?
Say that again.
I asked first, how can you have something without volume? You said you can have mass.
Yeah, and I said I think light also doesn't have volume, right? But light is a thing. Or is it not a thing?
But you guys say it doesn't have mass.
Yeah. Well, actually, I don't
So
know.
that's fine. It gets weird when you say it has no volume but with mass. That's the tricky part.
Well, it's a
I
field
mean, I
battery,
suspect
so it
it's
kind
kind
of
of the
makes
same thing.
sense.
Dude, they're still
They look
teaching the Bohr model in school. I was cleaning the science section a few weeks ago. This lady's teaching the Bohr model. It's like, come on, man.
You serious? They're teaching orbitals? No way.
Yeah, I asked her. I'm like, why are you teaching this stuff right in front of the kid? She's like, well, it's the easiest way, and they can get a grasp on what's going on. I'm like, I had to stop there. I was like, okay.
I mean, as far as like representing how chemistry works, it's relatively straightforward. Like it doesn't have to be. It's a model, right? It's not accurate in how like quantum physics actually works, but to know how like to get bonds and such, it's a
Oh,
relatively
dude,
decent way to illustrate it.
I saw the craziest friggin' thing with the double slit, bro. If you thought the double slit was weird, this shit is off the hook. Off the actual hook. Hold on a second.
Was it the infinite slits?
No, dude. They had guys. You know how they say if you observe which slit it goes through, that turns it into a particle? So
Yeah,
they
kind of.
had guys, meditators and shit. They had a whole bunch of people, focusing on the slit. They did this over a webcam, not even in the room and shit. You know what I'm saying? They just had the whole thing set up. Like they didn't have any detectors or nothing. And they're just having the guys focus on the slits. And it turned it into a particle, bro, without them even being in the room.
Yeah, I don't believe that.
Yo, they have a p value. They have it was sigma five that it wasn't an error. Like it was crazy, bro. I know you wouldn't believe it, but that's the thing. It was in the spirit science. Like I didn't go into the actual thing. I just saw it in a documentary. It was one of the spirit science ones. I forget which one. I could check my feed. That's freaking crazy. Now, what if that's true though? I know you don't believe it, but what if it turns out to be true? That would change everything.
It would, yeah.
Hey, let's carry on with whatever you guys are on.
I think we got there on that.
well, electrons, protons, and neutrons are field perturbations. So you guys were kind of getting on the topic of how do they have mass, no volume? Well, they're different shell
The
layers,
even
right?
crazier thing
Atoms.
is the even crazier thing is they say you don't touch anything. You never actually touch things. Like nothing's touching.
I remember that, Jeremy.
Crazy. That's crazy,
Yeah,
bro.
they
That
tried
makes
to
sense.
outline
Imagine
that
you
in the movie. What the bleep?
Yeah, imagine you punch someone in the face, you get hit with an assault charge, you're in court, you're in front of the judge. He goes, why did you punch the guy in the face or whatever? And the defendant is like, well, Your Honor, I actually never touched him.
I don't think that defense would fly in court.
Not guilty.
If you have scientific evidence that you never touched him, I mean, what, you know, how can you get charged with touching someone?
Just hire a
Don't forget,
quantum physicist.
don't
Yeah, forget a
forget,
lawyer. You don't need a lawyer. You need you just need a scientist to go in there.
They're gonna write a new law. Can't touch electrons.
That MC Hammer song, "Can't Touch This." He was on top of his game right there.
Oh wow.
Like that guy whose defense was he didn't actually kill the guy, he shot. It was the doctors who failed to save him.
Re?
It didn't work for
Or
him
you could
either.
have used the defense, since we never know what's actually moving. You could have just said, he came into my bullet.
Could try it.
He chest bumped my bullet.
Plus, the bullet never even touched the guy. On top of all that, the bullet never even touched him.
The guy that discovered electrons apparently was like panicking the next day. Thought he was gonna fall through the floor.
Dude, that's an actual thing, bro. They say if you slap a table enough times, eventually your hand will slide right through the table.
Yeah, there was a general who kept running into walls, thinking he could like phase shift through it.
Dude, there's a
Made
patent
a movie about it.
There's a patent for running through what the George Clooney Men Who Stare at Goats.
Yeah, that was a real guy.
Dude, there's an actual patent for walking through walls, bro. It's a patent. That's why I tell people, don't get too excited when you see a patent for something.
There's a bunch of real cool patents coming out right now. I mean, if you're on the hopium train, it looks exciting.
Well, if there's a patent for walking through walls, why did we spend 3 months just leaning on them?
A lot of leaners in the government, man.
No, I mean here we had like a 3-month discussion going on about, does a wall push back at you?
I was thinking of that just now too. I know.
Gotta watch out for
Well,
that
how much
wall.
energy does it take to push? I mean, according to you guys, the wall has infinite energy because it could just constantly push.
Well, not infinite. You put enough energy into it, it'll crumble.
No, I mean, if you just push against spend your whole life pushing against the wall. Your kid
Oh,
takes
I
over
see.
when you die. His kid takes over when he dies. You have generations and generations of people just pushing on this wall nonstop. They eat, sleep, poop right at the wall. There's shifts, multiple shifts. Somebody's always pushing on the wall. It takes energy to push. The wall just has infinite energy.
Well, what the deal was, Jeremy, is while you were pushing on one side of the wall thinking you could walk through, there was someone on the other side also pushing thinking he could walk through, and since you were both there, neither one of you could.
No, we can see the other side of the wall. No one's there. Nice try, though. Nice try.
I think the wall comes down in like first generation, unless it's just like some insane steel reinforced concrete monster.
Bro, it's just sheetrock. It's just a guy pushing onto sheetrock.
Is the point just the point of the wall pushing back, and like the idea? Like I actually didn't hear the beginning of this, so I don't get really get it.
Yeah, the wall pushing back is the issue. Yeah.
Oh, okay.
They say this is Newton's third law that we're talking about. Everyone knows that, right? They actually found a thing in sperm that debunked. What the fuck is this?
Whoa, my bad.
The whole first part of that robot, all I heard was a thing in sperm.
Hold on. This the pushing on walls is obviously Newton's third law we're talking about, and just Google it. They think that sperm debunked Newton's third law. There's this thing on the way sperm move that debunks Newton's third law.
You just make like for me, it like connects the physical model, how they say there's this electron boundary, right? So that's just that opposing force. That's that stiffness and rigidity. It's just the electromagnetic interaction between you and the wall. But people are just saying like it matters about the structural integrity of the wall. But if you look at the model, imagine it's a impenetrable wall. Like it just has that natural rigidity. That's just those electromagnetic forces. It is pushing back, but it's not unlimited. Right. I think that's a good point.
Bro, it could be a sheetrock. It could be sheetrock. You could just have a guy pressing on it. He does an 8-hour shift. Another guy takes over for 8 hours, and they have 3 8-hour shifts going for generations and generations. And if it takes energy to push, and the wall's pushing back, where's the wall getting this energy from?
Well, it's just the rigidity of the material, right? So like, I mean, eventually you'd have indentations from the push prints and all that stuff, especially on sheetrock. Like you would have wear and tear. Or explain your model a little better. I don't think I'm getting. I think you're seeing exactly how that makes sense, but I'm not seeing it.
This isn't my model. I don't think walls are pushing.
Oh, okay.
I think it takes energy to push.
I think that's a good claim to make because I mean, ultimately the law is dependent on the material, and sheetrock is. I mean, it's not gonna be this ultimate unconforming material, so you're gonna see the wear and tear, right? It's gonna
Yo,
cost it energy.
if Newton was a real guy and all the shit he did was actually happen, he was a fucking genius. Like, no doubt. He was probably the smartest guy that ever lived. But he just got some shit wrong, dude. Like, you're not going to get everything right no matter how smart you are. You're just not going to get everything right. Look at his law of viscosity. He got that wrong. You know what I'm saying? Like, he just got shit wrong, dude. There's little things that, even with boiling water, you could put it in a microwave, get it to 100, 200 degrees, and it's not boiling.
Yeah, there does seem to be an obsession with simplicity with Newton's laws. It's kind of the name of the game with the mainstream model, though. They're like, make it as simple as possible. Because you got to learn their language, learn their code method.
We got some things right. You didn't get everything wrong.
So, do you think it's reasonable to conclude that the moon is closer than the stars because it appears displaced compared to the stars for two observers in different locations?
I would say so.
What's that?
The moon appears closer than the stars because of what?
No, it appears displaced compared to the stars for two observers in different locations. Did you see the picture that Seafoam and I made last night?
I didn't.
Oh, let me get that for you. Alright, check that out. He's in one end of the United States, I'm in the other end, and we took pictures of the moon against the star background at exactly the same time, and then we overlaid them.
That looks trippy.
And so from that, we can calculate the distance difference between the moon and the stars, basically.
Basically just on size correlation?
No, parallax.
Do you have the two separate images?
I got my separate image. I don't have a copy of his separate image yet, except just from a picture of his phone, which was taken at a different time, or a picture of his camera screen, which was taken from a different time. I'll drop my picture.
That'll make a pretty cool stereogram.
Oh, it would, wouldn't it?
If you were to go about doing that, like if I wanted to recreate it, how would I like actually measure the position of it, like any proposed apparent star? Like how would I start with that for that position for the trigonometry equation?
I'm
Is there
not
a
sure
tool
I
for that?
understand the question.
Well, it's like if I want to use parallax to like measure the distance of a star, like how do I get the position of the star accurate?
Oh, I think they're all so far that it doesn't make a difference for something like the moon. In other words, the stars also are at different distances, but at this resolution, they all might as well be at the same distance, an infinite distance, because they're far enough away that even though they're technically in different positions relative to each other from our two different vantage points, it's so small that it's less than a pixel's displacement. So you need, they do measure parallax shift with stars, but they use extremely high resolution telescopes.
Very interesting.
But it's like, let's say you were out in a field, and 5 miles away was a line of trees. Or I should say a forest. And 100 feet in front of you was your friend. But you didn't know he was 100 feet. You could take a picture of him, step to your right 10 feet, take another picture of him. Now he's going to appear to have moved with reference to that line of trees back there, the edge of the forest. You won't be able to resolve any change in the forest itself because it's too far, and because you cannot observe any change within the parallax between the trees, then you know mathematically that it is so many times farther than your friend that you can consider it effectively infinite. But because your friend is only 100 feet away, he will have a significant parallax movement, and you will be able to tell how far he is away from you. Does that sort of make sense?
Yeah, it does.
So that's kind of what we do with the stars. I think Seafoam and I had a baseline of like 17,000 miles, and that was not enough to show any difference in the parallax of the stars against the stars. which means they're all way, way too far for us to, you know, detect their parallax, which means they're so many times farther than the moon that we can treat them for all practical purposes as infinite compared to the distance of the moon, and then we can resolve clearly the parallax effect of the moon. The important thing is that the parallax effect on the stars is almost nothing compared to the size of our baseline, but the parallax effect of the moon is significant compared to the size of our baseline.
I was trying to write down what I would do how you would do the equation. I'm getting lost at where I would do. So it'd be D. So if I did distance in parsecs for D and then PC for parsecs, I could do D times PC equals 1 over P times arc second. That's what the little manual's telling me here. So if I'm actually trying to do that equation, I'm using the standard like distance of a parsec, right? I'm actually having to take into account a standard, which is a starter distance of 1 parsec will have a parallax of 1 arc second. The distance to a star can be calculated using yep. That is so interesting. I'm gonna have to mess around with this.
It's sort of like this. Imagine you're in an airplane, a jet flying nice and straight, and you look way out 1,000 miles away. You can see a super bright light tower. It is not going to appear to be moving. If you wait long enough hours, it will, but because of that it's moving at the arctangent of the displacement by divided by the distance, it's a very, very, very slow relationship between you moving and its angle changing. Now let's say there's a treetop, a mile away or something. Let's make it 500 feet away. You can take a picture, and then after the jet's moved a little bit, take another picture. That lighthouse 1,000 miles away won't have moved in your frame detectably. The tree, however, will have. So you're basically just seeing the change in angle to the tree relative to the lighthouse, knowing how far you've moved between the two pictures.
Very cool. Who discovered this method of measurement? Do you know?
Parralax?
Yeah. I'll Google it. I'll Google it. The first measurement was made by a German dude, Frederick Bezel, in 1838.
Well, that was for stellar parallax. Parallax exists everywhere. You can do it in your house or on the ground, so it was discovered way, way before that. That's just when it was applied to stars, I think.
Yeah, you're right. That's the first time it was successfully used to measure a star, 61 Cygni, but as far back as like 1718, this is just not a great answer. It's, you know, some AI info dump. But Edmund Halley noticed the positions of some bright. Oh, I guess it was Edmund Halley in 1718. He's the first person to discover. He noticed the positions of some stars had changed substantially over time, which he attributed to what is known as proper motion, project of a star, or the projection of a star's velocity in the plane of the sky. And the breakthrough in measuring parallax came with the development of more precise instruments and the use of photography and astronomical observations. Ah, so it's like a combination of stuff. People had the idea, but then tech got good and they got to prove it.
Yeah, even owls use parallax. Have you ever seen how an owl shifts its head to the right and to the left?
Sneaky bastards. I'm not a fan of owls because of my cat.
Well, just watch a YouTube video when your cat's not watching.
Who?
Yeah, that's
How's it
cool.
going, John?